Thank you for the introduction, Glenn. And good afternoon, everyone. Again, my name is Mintan Hu. Today, I'm going to present our work for characterizing the reconfiguration latency of image sensor resolution on Android devices. So people are saying that continuous mobile vision is going to take off. Indeed. Enabled by more and more powerful hardware and more accurate algorithm and even more and more mature development platforms. Future continuous mobile vision is going to be revolutionary. And here is a simple example. It is a marker-based augmented reality application. And this paper is a marker, and an undergrad is standing on the marker as an object. So the algorithm underneath the application helps the application to determine the position of the camera. So when you are moving around the marker, you're actually moving around the object. This is only a simple example. You can obviously do more revolutionary things beyond this. And however, vision comes with high power consumption, especially for mobile devices. Your device is going to be hot and your battery is going to be dead really fast. And these are the numbers measured by running real AR applications on real devices, not actors. And we got a 2 to 3 watts power consumption, and they're relatively very high for mobile devices. So how people are dealing with the power efficiency issue? And traditional methods look for trade-offs. Here is just a classic example. We can either choose high clock frequency with high computing performance or high power consumption, or we can choose low clock frequency with low computing performance but low power consumption. Actually, people are good at utilizing all kinds of trade-offs to deal with different kinds of tasks. We kind of wonder, is there any trade-offs lies in image sensor resolution? And the answer is yes. By studying around our marker-based post-estimation application, we can compare low resolution with high resolution. Low resolution is better in performance and 1 magnitude lower energy consumption for processing each frame. However, the visual utility for low resolution is poor. You need to be closer to the marker or you need a bigger marker. And the accuracy is also bad for low resolution, but this can be mitigated by approaching the marker or just enlarge the marker itself. So we kind of want to utilize this resolution trade-off. And the system needs the capability to reconfigure sensor resolution dynamically to balance performance, accuracy, and energy efficiency. Sometimes, based on the distance to the marker, size of the marker, high resolution is necessary to ensure accuracy, like trillions of pixels. However, during the tracking, sometimes low resolution is already sufficient, and it is better for efficiency purpose. And then you may lose the marker again, and you want to shift back to high resolution and to low resolution back and forth. So by switching between resolutions, the sensor can balance the performance, accuracy, and energy efficiency. And the big problem here is that it takes too long to reconfigure the resolution. And again, these are the numbers measured on real devices. And surprisingly, we have a 400 milliseconds to 1,000 milliseconds reconfiguration latency. And this is resolution reconfiguration on real device. By the time I touch the screen to request a new resolution, until the first frame of that new resolution returned to the screen. We can see it takes some time, and during this time, the application is blind for some time. So our contributions in this paper, we profile resolution reconfiguration latency, and we find 3 sources inside the OS that make this latency. And we also propose several optimizations that to reduce resolution reconfiguration latency, and they are open for discussion. To profile the latency, our experiment platform is simple. We have an Android application which cycles through a set of resolutions supported by the device, And we installed Android open source project in which we injected all the timing codes to print out the timestamp difference between the start time and end time of each function. And we also got Google LG Nexus 5X device, and it got open source hardware abstraction layer. Before we can profile the latency, we need to define two latencies first. End-to-end reconfiguration latency and frame-to-frame latency. End-to-end reconfiguration latency is the time between the application requests a new resolution and the application receives the first full frame of the new resolution. And frame-to-frame latency is the interval between two frames being provided to the application, and the latter one is the first frame of the new resolution. The biggest difference between end-to-end reconfiguration latency and frame-to-frame latency is that shortly after the application requests a new resolution, there are some pending requests left in the processing queue for prior resolution, and the system needs to take care of that first. So the frames keep coming to the application. And in our experiment, we have an average of 400 milliseconds end-to-end reconfiguration latency and an average of 267 milliseconds frame-to-frame latency. Long end-to-end reconfiguration latency actually restricts the system from shifting the sensor between different operation modes. And longer frame-to-frame latency causes more frame to drop. So is it a hardware problem or an OS problem? We see that at hardware level, the end-to-end reconfiguration latency is 1 to 2 frame times. So if it is working at 30 FPS, it takes 33 to 66 milliseconds. And frame-to-frame latency at hardware level is actually 0 milliseconds. So compared with 350 milliseconds end-to-end reconfiguration latency and 267 milliseconds frame-to-frame latency, we're almost sure that it's mostly an OS problem. How's that? Because operating system is intricate. For example, this Android OS, it has several layers, including the application layer, framework layer, hardware abstraction layer, which is HAL, and Linux kernel, and all of them are sitting on top of the hardware. Each layer maintains the abstraction to different layers. However, interactions across different layers introduces extra delay. And in our resolution reconfiguration workflow, it involves all those layers, including the hardware. The application needs to send resolution request and consumes the frames returned by the sensor. And framework layer provides a service to create a capture session or process the capture request or result. And hardware abstraction layer provides the physical capability to configure the strings, which with the help from the Linux kernel, which touches the hardware driver fundamentally. In our paper, we measured the latency for all those major function blocks, and if you're interested, you can read our paper and find more information about this. So now we have profiled resolution reconfiguration latency, and we find 3 sources in the OS that make this latency. First, sequential configuration patterns, and second, expensive system calls, and third, imaging pipeline delay. So first, sequential configuration pattern. Whenever there's a new resolution request comes, the system is supposed to create a new capture session for that. However, this cannot be done immediately. The system needs to check for the pending request and process them first. And then after a new capture session is created, the system needs to create and configure new channels for it. However, again, this cannot be done immediately. The system needs to delete prior channel configuration first. So multiple checkpoints during the configuration workflow actually block the execution of other functions. which we call it sequential configuration pattern, and it contributes to a huge delay. And second source, expensive system calls. It is well known that system calls are expensive because of the context switch and I/O wait time. However, like system calls can be identified multiple times during channel creation and deletion. And also as a side effect of sequential configuration patterns, the combined cost includes the sum of each call latency. And the third source, imaging pipeline delay. As I mentioned before, shortly after the application requested a new resolution, the system is busy with processing pending requests. And after that, framework stops prior capture session and start a reconfiguration. After that, the first capture request enters the pipeline. At this point, the pipeline is empty and needs to be refilled. This generates a huge pipeline delay between the first capture request and the first capture result. Then we propose 3 optimizations to reduce resolution and reconfiguration latency. First, parallelize configuration procedures. And second, reuse prior configuration. And third, timely health control of channel management. So proposition 1, parallelize configuration procedures. While channel deletion needs to wait for processing the pending request, however, channel creation does not need to wait for anything. So we suppose that whenever there's a new resolution request, it can go to a configuration manager, and this manager will help to decide to create new capture session or continue or not to process pending request or hold or delete prior capture session in parallel. And proposition 2, reuse prior configurations. Since system calls are necessary for creating and deleting channels, so instead of creating and deleting for multiple times, we want to give HAL the controllability to hold and reuse prior configurations so that system calls can be avoided. This is especially helpful if the application wants to switch the operation between 2 different modes. However, we need to study the side effect as the memory requirement, power consumption, or some system overhead. And proposition 3, timely health control of channel management. Enabled by parallelized configuration, sensor resolution reconfiguration can be done while the system is processing for the pending request. Then the HAL decides when to stop the prior capture session and when the first capture request enters the pipeline. By doing this, the pipeline is always filled, and ideally there will be no delay between the substantial delay between the first capture request and the first capture result. By combining all of them together, this is our proposed resolution reconfiguration workflow. Whenever there's a new resolution request, the system starts the reconfiguration immediately, and then it decides to hold or reuse or simply delete prior configuration in parallel. We anticipate that end-to-end reconfiguration latency can be reduced to 166 milliseconds, which it enables smooth transition between sensor modes. And the frame-to-frame latency is reduced to 0 milliseconds. In other words, between resolution request and the first frame of the new resolution returned to the application will always have frames. To wrap it up, future continuous mobile vision needs the system to reconfigure sensor dynamically to balance energy efficiency, accuracy, and performance. However, current Android OS causes long reconfiguration latency, and we find 3 sources inside the OS that make this latency, and we also propose 3 optimizations that anticipate to reduce the latency. And we hope that we can enable new classes of vision algorithms that utilize the resolution-based trade-off to improve the performance and efficiency in a variety of related tasks. Thank you, and I'm happy to take any questions.